So I want to start today with, well, a bit of a reality check for everyone listening.
Okay.
Because we spend so much time obsessing over what AI can actually do. Can it write a sonnet? Can it code a website? Can it pass the bar exam?
Right.
And lately, the answer to all of those has been this resounding yes. But we rarely, if ever, talk about the actual cost of getting the AI to that point.
Yeah, and to be clear, you're not talking about the $20 monthly subscription fee for ChatGPT.
No, exactly. I'm talking about the sheer, brute force effort and money it takes to build these things in the first place.
Yeah.
I was reading through this stack of research you sent over this week, and honestly, it felt a little bit like looking under the hood of a Ferrari and realizing the engine is being held together with duct tape.
That's a surprisingly accurate analogy, actually.
Right, because we're seeing this massive pivot in the industry right now.
Yeah.
We aren't just building simple chatbots anymore. We're moving toward what they call reasoning AI.
Yeah, models that don't just blabber on, but actually think, plan, and strategize.
Exactly. And that is the big shift. We're moving from just prediction, just guessing the next word, to actual reasoning, multi-step problem solving.
But here is the catch, and this is exactly what we are diving into today. Training these reasoning models is incredibly, painfully slow.
And so expensive.
Unbelievably expensive. It turns out our current way of doing it is just wildly inefficient. We are hitting a wall where just, throwing more graphics cards at the problem isn't really working anymore.
But of course, there is a solution, or at least a potential massive breakthrough. So for this deep dive, we are looking at a brand new paper from a really heavy-hitting collaboration.
Yeah, researchers at MIT, NVIDIA, the MIT IBM Watson AI Lab, and ETH Zurich.
Huge names. And they've come up with a system called Taming the Long Tail.
And the headline here is pretty staggering. They managed to speed up the training of these complex reasoning models by anywhere from 70% to over 200%.
Which effectively means they cut the training time in half.
Or more, depending on the task.
And they did it without inventing a magical new chip. They didn't build a bigger supercomputer. They essentially they stopped the computers from being lazy.
Precisely. It is entirely a software breakthrough, not a hardware one.
So the mission for us today is to figure out exactly how they did it. We need to unpack what this long tail actually is, why these multi-million-dollar supercomputers are sitting around twiddling their thumbs, and how this new method fixes it.
Because if this works at scale, it changes the economics of AI completely.
Right.
It really is a glimpse into how we go from experimental AI in a lab to industrial scale AI that can run the world.
Okay, so let's set the stage a bit for everyone. You mentioned reasoning models, and I feel like that term gets thrown around a lot right now. How is that functionally different from the AI I use to, draft an email?
Okay, so think of your standard chatbot, like the early versions of GPT, as a really talented improviser.
An improviser, okay.
Yeah, you give it a prompt and it immediately starts talking. It is just predicting the next word based on probability. It's smooth, it's fast, but it's not really thinking ahead. It's just flowing.
It's basically confident rambling.
Exactly. It's very confident rambling. But a reasoning model is fundamentally different. These are models designed to solve complex, strict problems. Math equations, coding challenges, long-term strategic planning.
Right.
If you ask a reasoning model to solve a calculus problem, it can't just improvise a bunch of numbers. It has to break the problem down into logical, sequential steps.
That to show its work.
Exactly. It has to have a chain of thought. And to teach a model to do that, we use a specific training method called reinforcement learning, or RL.
Okay, let's stick a pin in that. Reinforcement learning, that's essentially the carrot and stick approach, right?
Essentially, yes. But the mechanics of it are really important here because that is exactly where our massive bottleneck is.
Okay, weigh it out.
In RL training for reasoning, you have a cycle. First, you give the model a prompt, let's say a really hard grade school math problem.
Got it.
The model doesn't just give you one answer and call it a day. It generates a whole bunch of possible answers, sometimes dozens, sometimes even hundreds of different attempts at solving it.
Like it's brainstorming.
Yes. And this phase is called the rollout.
Okay, the rollout phase. Throwing 100 ideas at the wall to see what sticks.
Exactly. That is the rollout. Then the system evaluates those answers. It checks which ones actually arrived at the correct final number. The ones that get the right answer get a reward.
The carrot.
The carrot. And this is the crucial part, the model updates itself. It tweaks its own internal parameters to act a little bit more like the version of itself that got the right answer.
So the cycle is basically brainstorm, evaluate, learn, and repeat.
Correct. Now, looking at that cycle, where do you think the massive delay is happening?
Well, I mean, I would naturally assume the learning part,
Yeah.
going in and rewriting the weights of a massive neural network. That sounds like the really heavy lifting.
And that is what almost everyone assumes. But the research from the MIT team shows the exact opposite. The learning part, the actual parameter update, is lightning fast.
Really?
Yes. The actual bottleneck is the rollout, the brainstorming phase. The paper states that generating those candidate answers takes up to 85% of the total training time.
Wow. Wait, so 85% of the time, this massive supercomputer is just listening to the AI talk to itself.
Pretty much. The system is just sitting there waiting for the model to spit out text so it can finally grade it and learn from it.
Okay, so text generation is slow. I
Yeah.
get that. But why is the paper called Taming the Long Tail? That sounds more like a statistics term to me.
It is, and it describes a very specific, painful problem in distributed computing, because to train these huge models, we don't just use one processor, we use thousands of GPUs working in parallel.
Right. Those huge server farms you see pictures of.
Exactly. So imagine a classroom with 30 students. The teacher, who is the central server in this analogy, gives everyone a math problem and says, solve this, but nobody leaves for recess until everyone is finished.
Oh, I hated those teachers.
We all did. Now, most of the students are average speed. They finish the problem in, let's say, 5 minutes. But maybe the problem given to one specific student is accidentally much harder, or that student just gets stuck. That one student takes 15 minutes.
So the other 29 students are just sitting there staring at the wall.
Yes, they are idle. They are just staring at the clock. And in the world of GPUs, this exact phenomenon is the long tail. Most processors finish their rollout generation quickly, but because of the random, unpredictable nature of generating text, a few processors take a really long time.
And because the system needs to synchronize everyone to do that learning update you mentioned.
Everyone waits for the slowest guy.
That seems incredibly wasteful.
It is massive. The researchers found that this idle time is the single biggest inefficiency in the whole training process. You have millions of dollars of hardware sitting there, burning insane amounts of electricity, doing absolutely nothing, just waiting for the long tail to finish.
Okay, so the problem is crystal clear. We have a classroom of bored genius students waiting on the slow kid. The obvious solution seems to be, well, give them something else to do while they wait.
Exactly. That is the core question the MIT team asked. How do we repurpose that idle time?
And this leads us to the first big concept they tried to use, which is called speculative decoding. Now, I have heard this term before in relation to making chatbots like ChatGPT faster for regular users. Can you give us the quick 101 on that?
Sure. The absolute best analogy for speculative decoding is the boss and the intern.
I like this. Lay it out.
Okay, so you have a boss model. This is your main massive reasoning model. It is brilliant, highly accurate, but it's very slow. It's like a meticulous author who agonizes over every single word.
Okay, the boss is slow but smart.
Then you have the intern model. This is a much smaller, lightweight AI. It is not nearly as smart, but it is incredibly fast. It can type 100 words a minute without thinking too hard.
Got it.
In a standard speculative decoding setup, if you want to speed things up, you let the intern write the first draft. The intern looks at the prompt and quickly guesses what the boss would probably say. It types out a whole paragraph in a fraction of a second.
And then the boss just signs off on it.
The boss reads it. And because it is computationally much faster to just read and verify text than it is to generate it word by word from scratch, the boss just scans it. It says, good, 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 wait, there's a typo here, fix that, good.
So you get the high quality of the boss, but closer to the speed of the intern.
Exactly. That is speculative decoding, and it works absolute wonders for inference meaning when you are just actively using a finished model.
Right. So why did they need to write a whole new paper? Why not
Yeah.
just put the intern in the classroom? When the fast students finish early, just have them switch to this intern mode to help the flow ones finish.
Yeah. See, this is the part where you usually ask me, what's the catch?
Well, I am waiting for the catch. Because if it were really that easy, NVIDIA would have just built it into the hardware 5 years ago.
The catch is that we are talking about reinforcement learning here. We aren't just running a static, finished model. We are actively training it. The boss is changing.
Oh, right.
Yeah.
The boss is constantly updating its own brain from those rewards.
Exactly. In RL training, the main model updates its internal weights thousands of times. It is constantly evolving its core strategy. So imagine the intern has studied the boss's style from yesterday. It knows the bot really likes to solve math problems using algebra.
Okay.
But then, 10 minutes into today's training run, the boss gets a reward, has an epiphany, and decides that using calculus is actually way better, the boss has fundamentally updated.
But the intern doesn't know that yet.
The intern is still frantically drafting everything in algebra, so it hands this massive draft to the boss, and the boss reads it and says, "What is this trash? I don't do it this way anymore."
So the boss just rejects the draft entirely.
Everything gets rejected. And if the acceptance rate drops too low, you're actually losing time. You are spending precious energy running the intern, and the boss just has to rewrite the whole thing from scratch anyway.
It's a moving target.
Exactly. In the field, it's called distribution shift. The statistical distribution of the boss's output shifts as it learns, and the static intern just gets left behind. This is exactly why, historically, speculative decoding has been considered completely useless for training reasoning models. It just breaks.
Okay, so the intern becomes useless because it's always out of date. Which finally brings us to the actual breakthrough of this paper. Taming the long tail, or TLT. How did the team at MIT actually solve this sinking problem?
They introduced two really clever innovations. The first one is called adaptive drafter training.
Which means teaching the intern on the fly.
Precisely. They looked at that idle time in the GPU classroom again. Remember those fast processors who finished early and were just staring at the clock?
Yeah, the ones burning up the electricity budget.
In the TLT system, the moment a processor finishes its main job, it doesn't sit idle for a millisecond. It immediately switches gears and starts training the small intern model.
Wait, so it's using the actual downtime to update the intern?
Yes. And here's the real magic trick. It trains the intern on the exact data the boss just generated in that very same batch.
So the intern is learning from the boss's brand new strategy literally seconds after the boss invents it.
Correct. It is real-time continuous alignment. The intern is no longer looking at yesterday's manual. It is watching the boss work right now in real time and aggressively updating its own internal logic to match.
That is brilliant. So the apprentice literally never falls behind the master.
Exactly. Because the intern model is so small, it learns incredibly fast.
Yeah.
So as the boss naturally drifts into new strategies, like switching from algebra to calculus, the intern follows right along smoothly.
Okay, so innovation number one is a self-updating intern. That neatly solves the distribution shift problem, but you said there were two major innovations.
Right. Innovation number two is called the adaptive rollout engine.
Adaptive rollout. Is this another AI model?
Think of this more like a manager or a really smart traffic controller. Because even with a fast-learning intern, sometimes the system just gets messy. Maybe the prompts in a certain batch are exceptionally hard, or the boss is just being extra picky.
So the intern's drafts might still get rejected occasionally.
Sometimes, yes. And if you just rigidly force the system to use the intern all the time, regardless of what's happening, you might still cause delays. So the adaptive rollout engine watches the whole process globally in real time.
It's monitoring the stats of the whole system.
Right. It looks closely at the acceptance rate, basically, how often the boss is saying yes to the drafts. It looks at the latency of the hardware. If the intern is on a hot streak and getting everything right, the engine hits the gas. It tells the intern, draft longer sentences, take on more of the workload, go, go, go.
And if the intern starts failing,
The engine instantly taps the brakes. It says, okay, the boss is in a mood, the drafts are failing, let's back off and just do standard generation for a little bit until the intern catches up. It literally optimizes the compute strategy for every single batch on the fly.
so it's never a static setting. It's totally fluid.
It's extremely fluid, and it ensures that no matter how chaotic the training process gets, the hardware is always being used as efficiently as possible.
So we have a fast-learning intern filling the gaps and a smart manager directing traffic. The theory sounds flawless. But we are talking about academic research papers here. Does it actually work in the real world outside the lab? But what were the actual results?
The results were stark, very clear. They tested this TLT system on major industry standard reasoning benchmarks, things like the GSM-8K dataset, which is a massive collection of grade school math problems, and really complex coding tasks.
What were the numbers?
They saw overall training speedups ranging from 1.7x to 2.1x.
Okay, hold on. 2.1x. That is literally more than double the speed.
Yes. Just imagine you are an AI researcher. A major training run that used to take you 4 solid weeks now takes less than 2.
That is huge for the bottom line of these companies. But I do have to play devil's advocate here. I'm a skeptic by nature. Usually in life, if you do something twice as fast, the quality drops. You have to cut corners somewhere.
That is the natural assumption, yes.
Did the models get dumber? Did the reasoning get sloppy because they rushed it?
That is actually the most important claim in the entire paper. They call their method lossless.
Lossless, meaning no loss of quality.
Zero drop in accuracy. The final reasoning model, trained with TLT, performed exactly the same, score for score, as a model trained the incredibly slow, expensive way.
How is that even possible? If the intern is doing half the actual typing.
Because the boss still verifies absolutely everything. Remember, the intern is just drafting. The boss, the main highly intelligent model, still has to read and approve every single draft based on the strict reward system. If the intern writes garbage, the boss simply rejects it and does it the hard way.
So the safety net is always perfectly in place.
Exactly. The core learning signal, the actual complex math that updates the brain of the AI, remains pure. It hasn't been corrupted or diluted by the smaller model. We just got to the exact same destination twice as fast.
Okay, that makes total sense. It's like taking a shortcut that leads to the exact same front door. You aren't breaking in through the window to save time, you're just running down the path instead of walking.
That's a perfect analogy.
So let's zoom out a bit. We've got the technical win here. But why should you, the listener, who might not be training massive AI models in your basement, actually care about this deep dive?
It matters for two massive global reasons. The first is accessibility. Right now, training these high-end reasoning models is an exclusive game for the ultra-rich. Google, OpenAI, Meta, it costs tens of millions of dollars in raw compute time.
Right. It's a very small, exclusive club deciding the future of AI.
But if you cut that baseline cost in half, suddenly you drastically lower the barrier to entry. University labs with smaller budgets can actually compete again. Smaller startups can afford to build specialized reasoning models for medicine or law. It democratizes the capability.
Okay, I really like that. More competition usually means better, safer tools for all of us. What is the second reason?
The environment.
Ah, right, the astronomical energy bill.
We talk a lot about the carbon footprint of AI, and rightly so. These massive data centers are becoming terrifying energy sinks for the grid. If TLT cuts the required GPU time by 50%, that is a direct linear reduction in energy consumption for training.
You're effectively getting the exact same super smart AI for half the electricity.
Yes. One of the lead authors, Song Han from MIT, was actually very vocal about this specific point. He pointed out that as we try to scale these reasoning models up, make them bigger and smarter to solve harder problems, the baseline inefficiency was going to kill us. Not just financially, but physically. We literally can't just keep building new power plants solely for AI. We have to optimize.
It's the difference between driving a gas-guzzling Hummer and a hybrid. They both get you to the grocery store eventually, but one is sustainable for the planet and the other simply isn't.
And in this specific case, the hybrid is actually twice as fast as the Hummer.
Which is the absolute dream scenario.
Mhm.
Now, digging into the research notes before we started, I saw something mentioned about a freebie, a sort of bonus benefit to this whole process. What was that about?
Oh, this is a really cool detail. So think about our intern model again.
The little guy working overtime in the background.
In a traditional training setup, once you finish training the big boss model and it's ready to launch, you basically just throw all the scaffolding away. The helper scripts, the extra tools, they're gone.
Right. The job is done. Clear the site.
But with TLT, remember that the intern has been training alongside the boss the entire time. It has seen millions of high-quality examples of perfect reasoning. It has aggressively aligned its own logic with a super intelligent model.
Wait, so the apprentice has actually become a master in its own right?
Exactly. At the end of the entire process, you can just peel off that small draft model, and it turns out to be a surprisingly powerful, standalone reasoning model.
So you get a buy one, get one free deal on AI models.
You really do. You get your massive, heavy-duty model that you run in the cloud, and you get a lightweight, highly efficient model that is perfect for running locally on a laptop or a phone.
That is fascinating. It's like building a massive skyscraper and realizing the temporary scaffolding you used is actually a perfectly good, fully furnished house you can just sell.
The researchers even noted that this distilled model is often significantly better than if you had just tried to train a small model from scratch, simply because it had such an incredible hands-on teacher guiding it the whole time.
So looking forward then, what does this actually mean for the industry? Because we know all these tech companies are currently racing to build agents, AI that can actually do real work, execute tasks, not just talk to us.
It completely changes the velocity of research because speed isn't just about saving cash, it is about iteration. If a scientist has a brilliant idea for a new model architecture and they have to wait a full month just to see if it works, Progress is agonizingly slow.
But if they get those same results in 2
They
weeks,
can fail faster, they can learn faster, the whole cycle of human innovation speeds up.
it really feels like the Wild West era of AI, where we just blindly threw billions of dollars and huge piles of chips at the problem is finally ending. We are entering the engineering era.
I completely agree. We are maturing as an industry. The focus is fundamentally shifting from make it better to make it smarter. And taming the long tail is a perfect example of that maturity. It's not flashy, it's not a shiny new consumer product launch, but it is the exact kind of deep structural engineering that allows the next massive leap in AI to actually happen
It's the plumbing, but it's the high-tech plumbing that keeps the whole house from flooding.
and ensures we can actually afford the water bill at the end of the month.
Exactly. You know, it's funny. Taming the long tail, it is such a technical, incredibly dry name for a paper. But the core concept is actually kind of inspiring to me.
How so?
Well, it's really about refusing to accept waste. It's about looking at a room full of the most advanced, expensive machinery on Earth
Yeah.
and saying, hey, you in the back, stop daydreaming and get back to work.
It is realizing that the idle time we usually just ignore or accept as a cost of doing business is actually our biggest untapped resource.
So here's a final provocative thought for you, the listener, to chew on as you go about your day. We live in a world that is completely obsessed with more. More computing power, more internet speed, more data centers. We always default to thinking the solution is to just build and add something new.
But often it's really not.
Right. This research completely proves that the next great breakthrough didn't come from getting bigger. It came from looking incredibly closely at what we already had and simply refusing to let a single second of potential go to waste.
It really makes you wonder what other vital systems in our lives, our power grids, our global logistics, maybe even our own daily schedules, are running at 85% inefficiency, just waiting for someone to finally tame the long tail.
That is a great question to end on. That's it for this deep dive. Thanks for listening, and we'll catch you on the next one.